Okay, so welcome to lecture 16 of the KF22 course. Here we are going to talk about the gauge symmetries and the corresponding interactions that it predicts. And for that, we will actually begin with what's called the global phase transformation for the charge scalars and the Dirac field. So let's start with the global phase transition in general. So what do we have for the case of scalar charge scalar? This is the Klein-Gordon Lagrangian for the charge scalar. This is del mu phi dagger del mu phi minus m square times phi dagger phi. Okay, and what the phase transformation is that phi of x is going to some exponential minus I alpha times phi of x. You scale, or rather you multiply this complex field with a constant phase throughout. So the change in the phase, that alpha, is independent of x, and that's the reason for the global, the phrase that we are calling it a global, and global phase that we are saying. So it's because it's the same phase for every single point, and if this is the transformation for phi, then the phi dagger transforms with the phase exponential I alpha plus I alpha over here. And likewise the derivative transform with the same exponential minus I alpha derivative of phi, and the derivative of phi dagger again transforms as exponential I alpha. So this gives that if the first term in the Lagrangian, which is del mu phi dagger del mu phi, the del mu phi dagger will give me exponential I alpha, and del mu phi will give me exponential minus I alpha. They will cancel, and so this term will remain intact. Okay, so and similar thing for phi dagger phi. Okay, the two terms will cancel, the two phases will cancel, and our Lagrangian density for the charged Klein-Gordon field will remain as it is, no change at all. Okay, so this is one invariance of this charge scalar Lagrangian, that this is invariant under global phase transformations, and this leads to certain conserved quantity that we'll discuss in a moment. Now for the Dirac field also, you have psi bar and psi appearing in the same term, okay, in each term of this thing. So here also we expect similar cancellation, and we will see that transformation is psi of x is going to I times, so exponential I alpha times psi of x, and that would amount to psi bar, which is nothing but gamma 0 multiplied from the right hand side to psi dagger. So this transformation of exponential I alpha actually happens with the psi dagger, and the difference between psi dagger and psi bar is just a gamma 0 from multiplying from the right hand side. Okay, and so this is this transformation over here. This thing over here gives me, for the del mu psi, it's the same exponential minus alpha term, and for del mu of psi bar, because it's del mu over dagger, you get exponential I alpha thing. Okay, so these are the transformation, and if I put those transformations together, then psi bar psi basically goes to psi bar psi, remains invariant term wise. Okay, and psi bar gamma mu del mu psi will also go to psi bar gamma mu del mu psi, because del mu psi will change with exponential minus I alpha, and psi bar will change with exponential I alpha, and it remains as it is. And just for completeness, I'm also writing this term where del mu psi bar gamma mu psi also goes to del mu psi bar gamma mu psi. This particular term usually is not written as a part of Dirac equation or Dirac Lagrangian, but I'm saying this here because this was the problem you did in the take-home examination for the mid-semester. Okay, so so even that Lagrangian, that complicated looking Lagrangian in the exam, which involves this last term, even that remains invariant under this global phase transformation. Okay, so that basically tells me that LD is going to LD, this Lagrangian density for the Dirac field is invariant under this phase transition, this change of global change of phase. Okay, not phase transition, phase transformation. And given this, in these theories, we can, using the Noether's analysis, using Noether theorem, we'll be able to find what's called charge, which is space integral of the 0th component of the conserved current. Okay, that will be a conserved quantity, and this basically is nothing but the charge of a charge field. For the charge scalar it is electric charge or whatever charge that it has, and for the fermion also there is a kind of fermionic charge that is conserved. And for kg case one can check, it is the expression for this density is given by this. This is one of the first few lectures we computed this. This was the motivation behind why we need the Dirac equation, where Dirac equation actually gives something which is necessarily positive, while kg equation can have a negative value of the density, and that is understood as a more negatively charged particle than the positively charged particle. Okay, so yes, these things are invariant under global phase transformations. Okay, and these are well-behaved theory with conserved quantities. Now we move on to quantities, to fields where we make the transformation to be local. Okay, it is local phase transformation. This is, technically speaking, is the right name for what we usually call the gauge transformation, because initially what people did, they changed the scale of this thing. So exponential without this I and alpha being real, okay, would actually exponential is a scale factor. It becomes over here, so so it will scale up or scale down the value of the field. But some of that, this is what people did for the case of gravity, where the actually scale changed, and that's why the name gauge theories. But technically speaking, it is a local phase transformation. So I'm writing this name over here just for completeness, but for entire rest of the course, in fact the title of this page, PDF page, is also gauge transformation, gauge symmetry. So we'll actually call it gauge symmetry afterwards. Okay, but since it's the first introduction, I'm calling it the local phase transformation, because that's what we are doing over here. Phi of x goes to phi prime of x. Okay, prime is not derivative, just another field. So phi of x goes to, transforms to phi prime of x, which is related to the original guy with exponential minus I alpha of x multiplying the phi of x. So alpha of x is a space-time dependent quantity. Okay, so that is the thing. What if alpha of x is space-time dependent? So phi dagger, given this is the transformation of phi, the transformation of phi dagger is phi dagger of x goes to phi prime dagger of x, which is just exponential plus I alpha of x times phi of, phi dagger of x, it should have been. Okay, so right. Okay, so I made the correction. So phi dagger of x goes to phi prime dagger of x, which is exponential I alpha x phi dagger of x. But what happens here is that del mu of phi of x will then go into del mu of phi prime of x, and if you put the value of phi prime of x, you will get this relation, okay, where the exponential factor is sitting. Now del mu can act on alpha of x, or del mu can act on phi of x. Using the Leibniz rule, we have two terms now. The first term, where the del mu acts on phi of x, is same as what we had for the case when alpha of x was space-time independent. So exponential minus alpha of x del mu phi of x minus I times del mu of alpha x, and then exponential minus I alpha x phi x. Okay, so this piece is the extra piece. Okay, so, and likewise I have del mu phi dagger. I can act on phi dagger as well. It will be going to del mu phi prime dagger of x, which is again, by putting this thing, gives me two terms. Okay, this is the extra piece. The second piece is the extra piece, because del mu of alpha of x is non-zero. Okay, so I get two extra pieces. So this Klein-Gordon equation, the Klein-Gordon Lagrangian, is not invariant under this, under what's called a local phase transformation, or which is I'm going to call local gauge transformation. Okay, so it's not invariant under this quantity. So if I want the invariance, okay, so I will remove all the terms which are culprit. In fact, it's a derivative term which is a culprit, because as we can see, phi of x goes to exponential I minus I alpha x, and phi dagger goes with the plus. So if I have a term like phi dagger phi, very nicely this thing cancel, no trouble. Only the derivative piece are problematic. Okay, so what we need is something. We need a covariant derivative, under which covariant means it varies in accordance with. Okay, so we need a derivative which varies in accordance with some similar law, okay, which means, and here's the covariance definition, so d mu of phi goes to d mu of phi prime, which can be written as exponential minus alpha of x d mu of phi. Okay, so like in the previous case, when the derivative also transformed in the same way as the field, okay, everything was well defined. So here we want the similar thing, that here my derivative does not transform in the same way. So I want to change the definition of derivative itself such that it transforms in a nice way that I want it to transform as. Okay, so the proposal is that d mu of phi of x, here's the proposal. Okay, so let me just unmark this. So here's the proposal: d mu of phi of x is some partial derivative mu plus some i.e. a mu, okay, acting on phi of x. And when transformation is happening, okay, when I'm making those transformation, then a mu of x goes to a prime of mu of x, which is related to a mu of x by this relation, which is a mu plus 1 by e del mu of alpha of x. Okay, so if a mu transforms as such, then this d mu has well behaved thing. So let's check that. So d mu of acting on phi of x is like del mu plus I e. So this not like this. This is like this goes to the prime variable, and the prime variable is written is del mu is just del mu. A mu becomes a prime mu, and phi becomes phi prime. Okay, then you put the value of phi prime and a prime over here, so you get this term. Now you expand it, so we have derivative acting on this will give me two terms. That's my term over here. When the derivative acts on phi, then it gives me exponential minus I alpha del mu phi x, and when the derivative acts on alpha, okay, then it gives me this piece. Okay, and then these are the two pieces coming from del, and these two pieces, last two pieces, are just these two terms multiplying with the exponential I alpha phi x. And you can see that the term here and the term here, the last piece, which came because of the transformation of a, exactly cancels each other. Okay, so I just have the first and the third term, where I take the exponential minus I alpha x outside the bracket, and then whatever left is nothing but the definition of d mu. So as if d mu of phi x transforms exactly as advertised, exponential I alpha x times d mu of phi x. Okay, so and same thing we can do over here with the psi field, fermionic field. Okay, and if I take the dagger, it just my apology. So when I take the dagger, it just becomes plus I alpha. Okay, sorry. Okay, and once I have this, I can combine a d mu with a gamma 0 in between, and then psi bar on the left. So same thing one can do for the Dirac-Lagrangian as well, that the ordinary derivative over here, okay, gets changed by this what's called covariant derivative. Okay, so with this introduction of covariant derivative, my Klein-Gordon Lagrangian has become this, okay, which is d mu phi dagger times d mu minus m square phi dagger phi, because phi dagger phi was invariant anyway to begin with, and this turns out to be invariant under phi going to phi prime of x which is defined as exponential minus I e alpha of x. Now note, I changed the notation. Earlier I was just transforming it with quantity alpha x. Now I multiplied an e over here. The reason I will explain in a moment. And once I multiplied with e over there, the extra factor of e is coming with alpha. Okay, so I don't need to define the 1 over e in the transformation, which I had in the previous page. Okay, a mu transformed with 1 over e del mu alpha. Okay, so by doing this, what I am making sure that the gauge field transforms without any information about the so-called coupling e. Okay, and e is a property of the field phi. So if it is a charged field, then it transforms with a charge e, then it transforms in this manner, and it couples in this manner, where d mu phi is defined like this, because here the appearance of e is also the property not of the gauge field but that of the phi field. That's how we are going to interpret. Okay, so in this definition, with this rescaling, what I get is that the gauge field remains independent of the coupling E or the charge of the field, and it is the field that transforms in accordance with how much charge does it have. Suppose it doesn't have any charge, it's a real field, then it must not transform, it should not become a complex field. Okay, in that case E is 0. Suppose the particle that I'm talking is not have positive charge but a negative charge, then E will change sign, so it will become plus over here, but it will become minus in the covariant derivative. Okay, so this relative sign that is to be noted. So E is the parameter. E is what defines the value and the sign of the charge of the field phi, while alpha of x defines the amount by which it is changing. Okay, this is the pure gauge transformation, and that's why it is appearing in the gauge field as it is. Okay, in the transformation of gauge field as it is. So with this definition, okay, I will say that gauge invariant theory can be written like this. Okay, now once I write this theory, we note that d mu already have a field, the gauge field a mu, sitting inside it. So it automatically kind of gives me a coupling between the gauge field and the scalar field that we have been talking about. So let's look at that. So what are the gauge interactions? Okay, so gauge interactions comes from only the kinetic piece, which is d mu phi dagger d mu phi. If we expand it, is del mu phi plus IE a mu phi dagger del mu phi plus IE a mu phi. Now expand this 2 times 2, there are 4 terms. So first term is del mu phi dagger del mu phi, which we had in the original charged Klein-Gordon field. Okay, Klein-Gordon Lagrangian. Then I have a term which is the cross term between a del mu phi times this a mu coming from the second guy, del mu phi dagger IE a mu phi, and the reverse cross term with a minus sign, because this dagger will become minus. And here we note that phi is a complex field, but a mu is a real field. I'll repeat that in a moment. Okay, why it is so? So it's because of the I defined in front. So it's a real field over here, and it's connects with del mu phi over here, and the last is a mu and a mu phi thing connect together, which is E square a mu phi dagger phi. So this is the term that we are getting, and we're just reshuffling it. The first term is as it is, del mu phi dagger del mu phi, and plus IE, just a moment, I think there was no dagger over here, yeah. So del mu phi dagger del mu phi plus IE a mu times del mu phi dagger phi minus phi dagger del mu phi. Okay, so one can say that a mu over here, this particular thing, a mu over here, kind of couples with a current. So I can call this guy as J mu, okay, in this particular case. And so here you can see is a phi dagger phi and a mu is there. So this is like a 3-point vortex with del mu being present over there. So del mu sometime acting on phi, sometime acting on phi dagger. So in momentum space it will become momentum, difference of the momentum between these two. Okay, and E is the strength of the coupling that is sitting over there, while the last term, which has 2 of a mu's, okay, a mu and mu, and I write G mu nu just to contract this, and 2 of the scalar fields phi dagger and phi with the coupling E square. So this 3-point vortex and this 4-point vortex are proposed or introduced by our gauge interaction. Okay. And similarly, in the case of fermions, we have psi bar gamma mu d mu psi, which gives me this extra piece over here when I expand it, and this is the coupling of a gauge boson, okay, with a pair of fermions. And again, if I use the language of current, then this a mu is interacting with J mu over here. So this is the expression for J mu psi. Perhaps E times psi bar gamma mu psi is the vector current, or first of all we know that it's a vectorial object, and it is actually the expression for the current that we also have discussed earlier while discussing the Dirac field, that the 4 current has this definition. When for 0 it is just gamma 0 over here, and it becomes psi bar psi. Sorry, psi dagger psi it becomes, and others are just the current that we already considered in first few lectures. Okay, so the A mu actually couples with this current, and as far as the interaction vortex, it is a 3-point vortex, psi bar, psi, and A mu, and the gamma mu will sit in the vortex in the Feynman rules, and E is the strength of this coupling. So now having this, okay, fields coupling over here, both in the scalar field and the fermionic field, it is natural to ask that do we have this field as a dynamical field? So of course this A mu, which is actually photon that we are considering in the back of our mind, is a dynamical field, and so we should have a kinetic Lagrangian for that. Okay, so the gauge kinetic Lagrangian is given, and that we already know from other courses, is given by -1/4 f mu, where f mu is del mu a nu minus del mu a mu, and where a nu is a 4 vector, or where the 0th component is a scalar potential and the other 3 components are the vector potential from the electrodynamics. Okay, and so under gauge transformation, f mu nu goes to f prime mu nu, which is del mu a prime nu and del mu a prime mu, and if you expand these terms in terms of the alphas, then one term, the first term has gives this particular term in alpha, and the second term gives this particular term in alpha, but these two are the second derivative of alpha with only the order of the derivatives changed, and they are usually equal and cancel. So in the cases when they are not equal is when alpha is not smooth. So here assumption, inherent assumption is that alpha is smooth enough that these two out of order derivatives are actually same. There are no singularities in any of the direction when you are taking the directional derivatives. Okay, so when these two cancels, it's back to f mu nu. So this is a second rank antisymmetric tensor which is invariant under gauge transformation. In this particular case, it's simply invariant, hence this Lagrangian is also invariant. Okay, this Lagrangian for the kinetic piece. Okay, but this is a very here we are using the information of what we know earlier. Okay, usually what is useful is to look at f mu nu in a different way, and people who have done gauge theories would realize that in gravity, people who are doing gravity already in GR course, they realize that they also talk about the covariant derivatives in GR, and then they talk about a curvature tensor which then appears into the Lagrangian. So what curvature tensor looks in terms of the covariant derivative is what f mu nu is going to look in terms of the gauge covariant derivative, which is d mu d nu minus d nu d mu acting on phi is defined to be I times E times f mu nu phi. So if I define this, expression will come out exactly the same. We can just check that. So d mu and d nu acting on phi, so I'll just write both things expanded. The second, the first piece here, just the expansion is there, nothing special is happening in this first step. The second step, again this del mu is acting on phi, this phi is taken inside, so again nothing great is happening. What happens in the next step is that this derivative now acts, okay, onto the first term, giving me this here, and the derivative acts on the second term, okay, it gives me two pieces. Okay, once when it acts on a nu, and second when it acts on the phi field. Okay, then comes the a mu piece. Okay, a mu piece with this del nu phi is just here, and the last piece is a combination of the last two guys which is sitting over here. Okay, now this is my d mu a nu phi. Now what happens that if you take the derivative in the reverse order, okay, the first term here d mu phi and d nu phi will also have derivatives in the reverse order, and we are assuming phi to be smooth enough, so that is same as this order. So when I take this difference here, this term cancels out, this term will cancel out because it's symmetric. This term is also symmetric in mu and nu, okay, because mu and nu commute. This is to be noted because when we go to something called non-abelian gauge field, this will not commute. Okay, so here they do, they are ordinary scalar field, so they will simply, they are ordinary real scalar field actually, so they will commute. So in the d nu d mu case, they will also cancel. Now these two terms marked here, they actually go into each other if I change mu into nu. Okay, so this is the third term and the fourth term. So when I take this difference, the third term here cancels with the fourth term in the reverse order, and the fourth term here cancel with the third term in the reverse order. Okay, only thing that does not cancel is this piece, which is IA times del mu A nu, which in the reverse order it will be del nu A mu. Okay, so here f mu nu will become, so f mu nu will not naturally come, expression for f mu nu is above over here. Okay, it will naturally appear over here. So this is one way to define f mu nu, which we will use later when we are talking about the non-abelian gauge field theories. Okay, so having said this, okay, and that this is the Lagrangian of our theory, we have to proceed further to complete the story. Is that for Klein-Gordon case, the charge scalar, the full Lagrangian would be d mu phi dagger d mu phi minus m square phi dagger phi minus 1 by 4 f mu nu f mu nu. And likewise, you take the Dirac field Lagrangian, and to that you have added minus 1 by 4 f mu nu f mu nu. So this is the pure QED part here. So this right hand side is QED, and the left hand side is what's called the scalar QED. Maybe I should write this. This is QED, and this is scalar QED. Okay, so this is what we have now. As we discussed earlier, that the behavior of d mu depends upon what particle it's acting on. Okay, so I say let psi be a fermion with a charge E. So that means the psi field transforms, is psi x goes to psi prime of x goes to which is equal to exponential IE alpha of x psi of x. So this is what defines that it is a field with charge plus E. Okay. Okay. Apologies. Yeah. So this is what defines the field to be a charged like that with a charge E, and of course then d mu phi is defined as we have discussed earlier, is del mu plus IE A mu acting on phi. Okay. Now let's just say chi be another fermion with charge minus E by 3. Okay, so minus E by 3 is a charge, so whenever you see E over there in the previous equation, you replace it by minus E by 3. So chi of x goes to chi prime of x equal to exponential plus I E by 3 alpha x. Okay, so that is small e is replaced by small e by 3 with a minus sign, and that says d mu of chi of x is del mu minus I E by 3 a mu chi of x. So this is how I'll write d mu acting on chi. What should be expression of d mu? It depends on what is the electric charge of chi. Okay, so that's how it will be acting, and that's how it will be transforming. So this is the transformation rule here, and this is the rule to write the corresponding covariant derivative. Now let's phi be a scalar with a charge minus 2e. Okay, so wherever you say e over there in the first case, you replace it by minus 2e. So phi of x goes to phi prime of x, which is 2e alpha of x exponential times the phi of x, and the derivative, the covariant derivative will have the minus sign times 2e. So this is basically charge that of the particle that is sitting over there. Okay, and then I can write the Lagrangian involving all three of them, which is this part is just the charge scalar. Charge scalar is minus 2e charge. Here is the charge first fermion with charge plus e, and here is another strange fermion with charge minus e by 3, and then 2. So this is the all free particles, not really free because they are interacting with the gauge field, and this last part is the gauge field Lagrangian. Now we have discussed the fermion quantization, and scalar quantization was discussed in the previous course. So only thing that is left is to ask this question: how do we quantize the f mu nu f mu nu? To that end, we just say let's start with the quantity which is only f mu nu f mu nu, like here. Okay, and we'll focus on some problem, and we will deal with that in the next lecture. So LEM, the pure EM, no other thing that it is coupled to, is minus 1 by 4 F mu. Now you just expand it. So minus 1 by 4 del mu a mu, and likewise in the lower. And when you expand all these things, so the first term with the first term is del mu a nu with del nu a mu. So here you see del and del are contracted. Similar thing happens when the second term of both these are the fourth term. Here del nu a nu and a mu is contracted. So the contraction pattern over here is same as the first term, okay, which is marked by this yellow line. So these two terms are same up to renaming of the dummy variables. And this cross term, where the first term with the second term here and the second term here with the first term over there, they have a different contraction scheme, okay, of the indices. So they add up to, but they are same with each other but different from the first one. So each of this term will add up, okay, and give me this, cancel one of the two over here. So now I have minus half del mu a nu del mu a nu contracted, and here del mu a nu del mu a mu, okay. Now if I just take common del mu a nu outside, okay, so that just rest of the term just becomes f mu. So this is just another way to write it. It becomes useful sometimes, okay. Now what I say that let me compute the functional derivative of this guy with regard to a dot rho, which gives me the expression for the corresponding field momentum. So I have four fields over here. A mu, for mu equal to 0, 1, 2 and 3, there are four fields, and corresponding to each one of them I have a field momentum which is defined using this formula over here, okay. Instead of mu I have used rho over here. So pi rho is del Lagrangian density by del a dot rho, okay, and a dot is nothing but del 0, so I can write it like this. And then I use here on the right hand side I have written some rules for the functional derivative, okay. So del of a mu with del of a nu is nothing but delta mu, okay. So only when mu is equal to nu that it should be 0, otherwise it should be 1, otherwise it should be 0. Now here both have upper index. If both have lower index, again it will be like this, but okay, of course the lower and upper index will change its places. But if one has lower index and other has upper index, and here I have made a mistake, let me correct it. So here nu is upstairs, okay. So del mu is lower, and by del a nu is upper, so that will give me g mu. So using this rule and similar rules for the del also, indices for del also, okay. So if I do that, then I take a derivative of this derivative on the first term over here first. So here two of these guys are there, so using Leibniz rules I'll get two terms here. So when del a with this derivative is taken with the first term, I get mu delta mu 0 and delta nu rho times this guy remains unchanged over here, okay. And when it acts on the second piece, the first term remains unchanged, and second one gives g mu 0 g nu rho. Now what g does, it lowers or raises the indices. So here in this case it lowers the indices and sets the value, while del, it doesn't lower or raise the indices, it only changes the value, okay. So here the first two terms come from the first term here, and last two terms comes from the last term over here, okay. And when I do all this summations and replacement, what I get is del 0 a rho minus del rho a 0, okay, without any half, because the first two terms are basically identical. It will give me factor 2, okay, and which will cancel the factor half outside. The second term is the same, so basically you get this number that pi rho is equal to minus of f0 rho, okay. So this is the situation. Now it's all fine. I found the pi of the field, and why I need this is because first I need to convert the Lagrangian into the Hamiltonian. That's what we did for the scalar and the gauge case and the fermion case. So gauge case is no different. So we'll first convert into a Hamiltonian, write down the Hamiltonian in terms of the mode expansion with A's and A daggers, and then we go on to, that's the step of second quantization. But the problem over here is that the Hamiltonian density h, which is a function of a mu and pi mu, as a canonical conjugate variable that we are trying to construct, but the problem we hit is that pi 0 is 0, okay, because f mu here is the antisymmetric tensor, so rho is 0 means f0 0, and f0 is simply 0. You look at the expression over here, it's del 0 a0 minus del 0 a0. Okay, so pi 0 is identically 0, so I don't have the momentum corresponding to 1 degree of freedom. So what do we do? Basically, I will question this thing, can I still write the Hamiltonian starting from the Lagrange? And the answer is no. That thing is not unique, okay, and such Lagrangians are called the singular Lagrangians. You cannot do the Legendre transformation over here because one of the variable is identically 0, one of the momenta is identically 0. Okay, so how do we quantize it if I can't even have the Hamiltonian? Well, just, first of all, in the next lecture we'll discuss the certain features of the gauge theory and what do we need to handle them, and identify the correct degrees of freedom, because as we can see already that a0 is a strange variable because the corresponding moment of pi 0 is identically 0. So if pi 0 is 0, then I won't be able to find out the time evolution of a0 eventually, because usually pi 0 should be related to a dot, and there is no a dot in the Lagrangian, so as if a dot is completely undetermined or determined by something else. So time evolution of a0 and hence other fields can also be suspect. So we'll discuss all these topics in the next lecture, and there we will see how to identify the correct degrees of freedom and then go on to quantizing them. We'll briefly sketch what we do over here in the next lecture, and my favorite way of quantizing is actually the path integral way, so I will postpone most of the detailed computation and the final propagator computations for the path integral formula, although I will write what the propagators would look like over here as well. So with this we'll finish this lecture reasonably quickly, because I didn't have to waste my time writing things, although I made a couple of corrections over here. So hopefully this way you will also save time while going through these lectures, and you will have the slides. Let's hope this works out best. See you in the next lecture.